So welcome, everybody. I am Noelle Norton. I am the Dean of the College of Arts and Sciences, but also a professor of political science here at USD. I want to thank all of you for attending tonight. This is one of many events that we are going to have with our special guests this evening. So if you love this evening, I think Thursday night there's another one. And if you want to see it again, come again on Thursday. So before I turn the floor over to Perla Myers, who will give you a very detailed description of who our guest speakers are, I'm going to tell you about what this special event, how it got started. This is one of 3 Knapp Chair for the Liberal Arts events that we have hosted this year and have hosted since the 1990s here at USD. The Knapp Chair in the Liberal Arts was established in 1995 through the generous estate of Mary and Churchill Knapp. They were local residents and longtime supporters of the College of Arts and Sciences at USD. The funds from their estate gift enable the college to bring campus distinguished scholars from 3 divisional areas: arts and humanities, the natural sciences, and mathematics and social sciences. And they also keep the Humanities Center running, so this is how we're able to do that. The Knapp Chair contributes to the strength and vitality of the liberal arts at our university by teaching and interacting with students, collaborating with faculty, and presenting public lectures that engage our campus and local community in confronting humanity's urgent challenges. This year, the Knapp Chairs included, they've already left us, but Mario Romero of the University of Sao Paulo, Brazil, Linda Tuai-Smith of the University of Waikato in New Zealand, and tonight's presenters are Erik Demaine and Martin Demaine. Erik and Martin are a father and son team, and you'll be able to see that when they come up, and they're from the Massachusetts Institute of Technology. Martin Demaine is a robotics engineer and is the Angelica and Barton Weller Artist in Residence in MIT's Department of Electrical Engineering and Computer Science. He is an artist and computer scientist and started the first private hot glass studio in Canada. He has long been known as the father of Canadian glass, if you weren't aware of that. Erik Demaine's research interests range throughout algorithms from data structures for improving web searches to the geometry of understanding how proteins fold to the computational difficulty of playing games. He received a MacArthur Fellowship, that's the Genius Award, and as a computational geometer, tackling and solving difficult problems related to folding and bending. The father and son team work closely together and collaborate with scholars around the world on cutting-edge interdisciplinary work in folding and its connections to many different fields and areas. We are delighted to have them with us here this evening. And at this point, I'm going to turn the floor over to their host, who is the faculty member who conceived of the idea of bringing them and nominating them to be the Knapp Chair. And this is Perla Myers from our Department of Mathematics.
Actually, this was a team effort. So I'd like to thank, first of all, my co-schemers in the Department of Art History, and Architecture, Daniel Lopez Perez, and Odesma Del Rimpo in engineering, and Satyan Devedos in mathematics. Thank you very much for scheming. It's been really fun doing this to get Marty and Erik to come here. We're so excited. The students met them this morning and they were starstruck. So we're all really excited that you're here. Thank you to the College of Arts and Sciences, to the Humanities Center, and I'm going to say a few words about Marty and Erik. Then I will introduce Marty, and then Satyan will come and he will introduce Erik. And I will not say, Noelle just really said some of the bio sort of things, so I will tell you a little bit more how I met them. So I first met Erik and Marty Demaine when I went to the 2010 International Conference of Origami in Science, Mathematics, and Education in Singapore. I was super impressed by their work, their presentations. I thought they were incredibly engaging. And I was really inspired by their playful approach to their explorations. I thought it was really neat that they worked with hundreds of collaborators. One of the things I most remember about that conference was a little video that they showed where Marty was inside a big cube. It was a die. They were doing explorations of die rolling. And so they showed this little video, and Marty was in the die with a helmet, and Erik was rolling him around in this die, turning him over. And every once in a while, you would hear a little or something from Erik, and he said he wasn't too damaged from that. I thought it was silly and playful and funny and mathematical. And I think students don't get enough opportunities to laugh and be silly with mathematics. I think they should do that more. So Noel just sort of shared the words I was going to share about Marty, so I'm going to skip those. What impresses me the most about Marty is his mentoring ability and his enthusiasm. When I went to the conference in Singapore, I was with my 17-year-old son, and I was particularly touched by the bond and partnership that Erik and Marty had. Marty also seemed to take an interest in nurturing the younger participants of the conference, and I know my son had several really impactful conversations with him. And of course, anyone who is kind to your kid rises immensely in a mom's eyes, right? So in 2014, I took a group of students from here to a conference in Japan, and Marty took the time to really talk to them and provide them with valuable mentorship. He also came here and informally walked around campus for a while, and it was really neat. Basically, he somehow managed in the few minutes that he spoke with them to have them reflect and have some aha moments and share some insight. So I was really impressed by that. The mathematics department awarded Marty in, I guess, a year and a half ago, the title of Research Associate, and we're very honored to have him.
So one evidence of mentorship is whether the father can mentor his own son. And he's done that in spades. So I just want to say a little bit about Erik. I met Erik first, and I got to know him a little bit. Erik got his bachelor's at the age of 14. He was dragged around Canada. His dad just drove him around to different schools and found out that he just was soaking up things like a sponge. And so, Marty took it upon himself to mentor his son this way. And by 14, he had his bachelor's. By 20, he had his PhD. MIT gave him a job at the age of 20. And the youngest professor there at that time, and I think ever. Just a few years later, in 2003, Erik won the MacArthur Genius Grant. You get a grant just for being awesome. That's great. He was awarded the Guggenheim Fellowship in 2013, the Pressburg Award, 2015, the Nerode Prize. I could just keep going. 2017, the Fellow of the ACM Association of Computing Machinery. Their works have appeared in the permanent collection of the MoMA, Museum of Modern Art, along with documentaries and PBS and numerous other things. But, I'm a mathematician, so I'm going to get a little nerdy. So that's great in an overall thing, but just in technical things, some of the things you're going to see today is about origami and folding and glassblowing, some beautiful things about art, but there's an incredibly deep technical side to both of them. And some of the things that Erik particularly has worked on as a computer scientist and a mathematician are issues with complexity, how hard it is for a computer to compute something. A lot of things are related to what it means to even think and solve a problem. When is a computer a computer? These are really fundamental questions. Issues of approximation, how good is close enough? Issues about playing great games of Tetris and Mario Kart. These are all really important things. And just caring about puzzles. One thing I personally dream about is bringing back the Renaissance again as a liberal arts school. How do you bring the world where the walls between the sciences and the arts and the humanities go away? And I think the best example I see of them, the evidence I tell my students and when I give talks, is to look at both of them together as the example of bringing back Da Vinci again, what it means to look like that. If you want to taste more of what they're doing, during this entire week here at USD, we have 2 sites. We have some in Tijuana. We have some sites all over Linda Vista where students from elementary school, high school, architecture professionals, and the community is working on building and playing with paper and ideas motivated by the work of Erik and Marty. Personally, I wrote a paper with Erik, I think in 2003, a long time ago, on the foundations of origami design. It turns out that it is the least useful of all the papers Erik has ever written. But I'm in, baby. It's good. Without further ado, Marty and Erik Demaine, thank you so much.
Well, thanks. It's a pleasure to be here. I'm Erik.
I'm Martin,
and
sometimes called Marty.
and we come from different backgrounds. I come from a more math computer science background.
I come from a visual arts background.
But we've known each other a long time. and
I've been working with Erik longer than anyone else.
It's true, even longer than Satyen. So we have taught each other a lot. We're now both artists and both scientists, and we like to play together on both sides, and especially we like to work in areas where we can simultaneously do art and mathematics and science. And today we'll be talking mostly about origami, which is a great setting for doing that because there's a lot of geometry, but also a lot of art and sculpture possibilities.
One of our goals in working in these 2 mediums together, art and science, is to try and merge them. And eventually, we hope you won't be able to tell which is which, that they're both art and science together.
So we're going to give you a lot of examples of that, but first we're going to start with a little background, how we got here. So our story starts with the Martin Demaine Glass Studio in northern New Brunswick, Canada.
I was taller in those days.
Yeah, looked a lot like I do now, but so he had the first glass studio in Canada, hence the father of Canadian glass. He was commissioned to make goblets for the Queen of England. I think you made this out of window glass you melted down.
Right. In those days, we didn't have the technology to make glass ourselves, and so we started by melting down plate glass windows, broken windows, and later graduated to
making your own glass formulas. Right. This is before everyone knew how to do this. So then I came along, and our first collaboration was when I was 5 years old here. I've changed a little bit. Marty looks still the same as he does today. And we made these wire take-apart puzzles and sold them to toy stores across Canada.
The Erik and Dad Puzzle Company, and we split all the money 50-50. I still owe Erik a little bit.
Waiting to collect. Then we traveled a lot, as Satyen mentioned, mostly east coast of the United States, some in Canada. Born up there in Halifax, and this is an opportunity to try out homeschool, which worked out really well. And we would, instead of a sort of traditional schooling environment, we would learn from our neighbors and whoever was around us.
And it started fostering a goal of collaboration, that we could learn from others and we could kind of teach them at the same time.
And that's represented in our mathematics work, where we have over 400 co-authors. Find Satyen right there. And it's a lot of fun to work with lots of different people. And this collaborative spirit is more common in mathematics. We're trying to bring it more and more into the art world as well. We've been at MIT the last 17 years.
And the goal of this building, it shows that it's kind of a sense of play for us. This is where we're housed, and it's filled with, it's a playground, totally. And good students.
So there's lots of toys, we call them, for building robots and serious things, but also for building art and sculpture. There's a glassblowing studio at MIT for art glass, all sorts of great things. So we're going to start with origami, and we'll get to some more glass work later on. We're also both glassblowers now. And this is a fun documentary, if you haven't seen it, called Between the Folds, about the art and science of origami. And art and science is all around this field. Origami is very old, possibly millennia old, but at least 3 or 4 centuries old. This is one of the first books showing the technology of the late 1700s, which is to fold 3 cranes out of 1 rectangle of paper with 2 slits cut in it.
And that's kind of important that origami originally allowed not squares, cuts, and glue. And this is kind of an example, and it was in the US where we changed the methodology to make it squares and no cuts.
Thanks to the minimalism movement now, the model is 1 square, no cuts. So of course the things you can make are much simpler than this, as you might imagine. In fact, there was an origami design revolution in the, I guess, 80s to 90s, and it's continuing today, where every year we see more and more incredible, complicated, beautiful origami designs.
This is kind of a year where it started to peak. Each one of these is made out of 1 square of paper. The top one was made over a period of a year, not totally continuous, but took a year to do all those little scales. And same with the bottom one. I don't know how long that one took, but they're examples of you can do anything.
Here's a little design competition from a few years after that to fold a sailboat. Lots of different types. Maybe most technically challenging here is a sailboat with the sails closed. Again, 1 square paper, no cuts. This is folded from a piece of paper. It's green on one side, white on the other, so it has a color reversal. And this is a boat that's been cracked in half by a giant kraken, and the boat and the kraken are from 1 square paper. This is the crease pattern. The top 3 were all MIT students. And this is some more recent work, just crazy, beautiful, awesome things, all from 1 square paper, no cuts. How is this possible? Mathematics and algorithms. This is an example by Jason Koo, who was my PhD student, is now an instructor at MIT. But when he was a high school student, he designed this butterfly. And he didn't just sit down and start folding a piece of paper and hoping that it ended up to look like a butterfly. He thought about which parts of the paper should be used for which parts of the model. And there's a mathematical theory for how to do that, which all complex origami designers know, even if they're not thinking like a mathematician or they're not using computer software. They're using the geometry that's intrinsic to paper according to this theory called the tree method of origami design. And here's a sort of mathematical version of what it does. You, as input, you specify a stick figure for what you'd like to make. And you can specify how long these lengths are relative to each other. For the mathematicians, this is a metric tree. And then the goal is to fold something whose projection is that tree. So it has a flap for each segment down here, and the length of the flap should match the length of the segment. So if you give this to, there's free software that implements this called Tree Maker by Robert Lang. You plug it in, and you get the best way to fold a square piece of paper into that tree. So if you were folding a lizard, you could then shape that into a lizard. Here's a more complicated example from Robert Lang's Origami Design Secrets book if you want to learn more about this. So maybe you want to design a scorpion. You abstract that into a stick figure. You give that to the computer. It gives you this crease pattern, which folds into this thing, which is hard to see. There's lots of layers on top of each other, but it has 1 flap for each of these segments. And then, a little bit of shaping, and you can fold this into a scorpion. Easy.
One of the interesting things I find is that when an origamist starts to use the software for design, in about 6 months, he stops using the software, that he has the algorithms in his mind, and he can just sketch and draw and create patterns much like this, all by hand.
Yeah, this doesn't really have to be executed by a digital computer. The human computer can do it as well, and it's pretty intuitive and natural. It's quite difficult to prove that it always works, and Robert Lang and the 2 of us have been working on that for the last 12 years, it looks like.
Only 12 years.
Almost finished. So that's challenging. But also, from a geometric perspective, you might wonder, well, it's nice to make any stick figure, but can we automatically design the full origami thing? And so we started working on this way back in the late 90s. This is the first paper to use the word computational origami. And we asked, can you fold any shape? If I give you a square piece of paper, can you fold any polygon? This is not to scale. This square would be bigger. But what if a piece of paper is white on one side, black on the other? Can you fold any two-color pattern made out of polygons? Or more generally in 3D, can I make any polyhedral surface? And we proved way back then that the answer is always yes for a
But
large enough
unfortunately, it
piece of
takes a
paper.
lot of paper, a
Yeah.
big piece.
So we might take a piece of paper the size of the moon and fold, a small horse. So it's at least possible, but the challenge remained how to find a practical way to fold any shape. We have now one practical way called Origamizer. This just was finished last year with Tomohiro Tachi in Tokyo. And this is an algorithm and computer software, again, where you give an arbitrary 3D model. You convert it into a crease pattern. You fold the solid lines one way, the dashed lines the other. I didn't draw the square, but you would fold this from a square of paper. And about 10 hours later, you get your folded bunny, exactly what you want. And this works not just for paper, but any material that can hold a crease. This is Tomohiro folding a laser-cut sheet of steel with some extra holes cut out because steel is a lot thicker than paper. You can maybe recognize our building at MIT. This also took about 10 hours. But in the end, we get a steel bunny. So this is an exciting alternative way to manufacture things. Instead of shipping a 3D object, we can ship a flat thing and then just have an origamist fold it into the thing it's supposed to be.
In 10 hours.
This would be great for employment of origamists, I guess. We'll talk more about getting the sheet to fold itself into the 3D thing later. But it's a cool way, especially for making thin, lightweight structures. If you want a hollow object, origami is probably a good way to make it.
The other point of that one is that it was done with rigid material. It didn't
Right.
have to be flexible paper to do it.
Yeah, so the steel is exciting because it can be a lot more structural. Tomohiro, actually, his background is in architecture, and he's excited about making building scale objects. And he does build those things. This is Tomohiro again. There's another documentary recently in Nova called The Origami Revolution, and it coincided exactly with the release of Origamizer, the final paper. So that was a lot of fun, and you can watch that if you want to learn more. But we'll tell you about other different origami design things. This one comes from another art project where a friend of ours had a new result about to come out in Nature about how the DNA folds within the cell.
So this was designed to go on the cover, but we did not get the cover. But we got an incredible result that turned into many things, and this is the complete.
So this is an example of folding a space-filling curve. This is the Hilbert curve for the mathematicians, kind of out of a square of paper that happened to be printed with human chromosome on it. And we figured out this crease pattern, and it was supposed to represent how the genome folds within the cell of some space-filling curve. But we realized after folding this that we could generalize it and really fold any maze, any orthogonal graph.
So taking, we reduce it 1 to 3 when we fold, which is actually pretty consistent. And what's nice about these foldings is you can join any number of them together without increasing the complexity. But as they get big, it gets complicated.
Yeah, if you wanted to fold this maze, for example, this would be the crease pattern. Don't try this at home. It's a pretty big one. You can make it smaller. You can type in your favorite message, USD here, and fold that out of this crease pattern. It's kind of a puzzle here, like what does this spell? It's not so obvious unless
But it doesn't take too long to start recognizing different shapes because they're all kind of modular.
I used it to advertise my class at MIT. Everything is a number, so 6 here means electrical engineering, computer science, and 849 is the folding class. And this shows the kind of computational origami design process. You start with your conceptual design of what you want to make. You use an algorithm to automatically design how to fold it. And then you still have to manually fold it at this point, in this case with a couple of students. This, I think, was about 2 days to fold. It's pretty complicated. But it gives you the idea of sort of end-to-end computational origami design. And this class, while we're talking about it, is freely available online. You can stream all the video lectures and learn all about the technical stuff behind what we're talking about.
This is one of my favorites. It's a traditional art thing of combining yes and no. So we took the folding, that crease pattern's up there, and there's some secret letters that you don't see right away that when it's folded together, brings together the shadow of no. So it's a yes-no art piece.
This one you can fold.
Right, this is a reasonable one.
This one I hope you will never fold. But same idea, you've got the little gray regions that don't look like much up top, the crease pattern that fold into the 3D structure of science with the shadow of art hiding in the background. And this one is on display at the gallery here, this as a print. And this is one example of a whole series of mathematical and puzzle fonts that we design. We've been designing a lot of them recently and over the last decade or so.
One of the goals of these is to kind of expose people to research that we're working on. And also for us, when we start doing a font, it represents a problem that we're studying, we haven't solved, and it helps to do this back and forth to kind of develop intuition.
So each of these fonts invites the reader, the literal reader, to engage with some mathematical concept. Just even in some cases, just to read the text that we've written down, it's like a puzzle to figure it out, and you have to engage with the mathematics to do so. But in designing that font, we get to engage with the mathematics also and learn our problems better. And we'll be showing a bunch of these, not all of them though. So if you want to check out more, you can go to our website. Another way we like to express mathematics to the general public is through puzzles. So we also have a lot of folding puzzles available online. And each of these is based around a mathematical theorem or open problem. Let's see, this is about
Map folding.
map folding, which we've made some progress on, but it's still open. This is based on a kind of pattern folding puzzle, which is more or less solved. This is based on a polyhedron folding puzzle, which is kind of like Origamizer. This is based on a problem called turning inside out, which is still open.
Still wide open.
So there's a lot of fun here. And this is also, talking about puzzles is an excuse to mention a series
latest.
of 2,600 puzzles that we just released last week. And it's based around this font design. These are called sliding coin puzzles, and you can play them online at this website, coinsliding.erikdemaine.org. You can pick up any coin and move it to a position that's adjacent to at least two others. That's the rules. Your goal is to transform any letter into any other. And so there's 1,300 of these puzzles within each font. These are the current records. You'll notice a lot of them are still infinity. So you can set your record just by solving one of these puzzles marked infinity. There's a lot of them, so it's taking a while to solve all the puzzles. And this is kind of fun because we can prove that these puzzles are solvable even though we haven't solved them all yet. That's the power of mathematics. But let's go on to magic. So this is a fun problem. It's a long history, as we'll talk about. You start with a rectangle of paper, and you fold it flat however you like. You take your scissors, and you make one complete straight cut.
Ooh. We first came across this in a book by Houdini, where he did a 5-pointed star.
Here I've got an isosceles triangle. Very impressive. And it's actually 5 of them. And then we've got everything except those 5 isosceles triangles. Okay, this is like a slight improvement over the Houdini trick. I think we have some history here. This is the oldest reference we know is this Japanese puzzle book from early 1700s. And this is the question. It says, can you cut this emblem shape off of a piece of paper by folding a one straight cut? And the solution's on the right. And there's this story. Do you want to describe?
Yeah, we don't think it's true, but in 1873, there was an article in Harper's that the reason our flag has 5-pointed stars is that Washington wanted 6, and Betsy Ross came in and said, I can do 5, and showed how to fold a piece of paper.
There she is folding a piece of paper flat, making one straight cut, and there's the results, and making a 5-pointed
Just like
star.
your paper on the floor.
Now, you can do this for 6-pointed stars, too, but
That's quite easy.
but it's another early reference, at least, even if it's not true. So here's another fun example. So I've got this rectangle of paper. I folded it along that crease pattern. Maybe you can tell what it's going to make. If I cut along one straight line.
Yeah, it should be obvious.
Yeah.
Any guesses?
In this case, we get swan. Here's what that looks like. And let's do some more. Got a little angelfish. Okay, I guess you guys aren't impressed yet, so do one more. No, please.
We first learned about this problem
Butterfly.
from an article by Martin Gardner. Wow.
Go ahead. you were gonna say.
Oh, we first learned about this problem by reading an article by Martin Gardner where he talks about this. And he asked the question, what can you do? What can you do with folding flat and making one straight cut?
And what are the limits of this process? Turns out there are no limits. You can make any planar graph, any collection of cuts you want simultaneously by folding in one straight cut.
What Erik doesn't mention is I worked on this problem for almost 10 years until he got old enough to help me solve it.
That's why he had me. Of course, there's a font for that. You can take a square piece of paper, fold, and make one complete straight cut and make any letter of the alphabet. So you can, again, write your favorite message like USD here and get, this is the crease pattern to fold, and these are, in this case, there's a nice sequence of steps to do the folding. And if you click puzzle font, then you can surprise your friends. It's not clear this is going to make USD, but it does. What else? So all this folding, is very tedious to do by hand. Could we get a robot to do it? And the most success we've had in this direction is by making the sheet of paper itself the robot. And so in this case, there's little muscles in the paper, shape memory alloy, that when you heat up, pulls the creases shut, and you can make your little origami table completely automatically. Now, when we're building a device like this, if we design what we're going to fold with Origamizer, then every different shape we want to make, we need to build a completely different robot. So the idea here is to fold this grid pattern, which is in some sense universal. It's one crease pattern to rule them all. If you have an n by n grid with alternating diagonals, this is called box pleating in origami, then by turning on some of those creases and not others, you can fold any structure made out of roughly n cubes. So if you have some 3D shape you want to build, you approximate it with little cubes in the same way that we pixelize images. We voxelize 3D volumes. And then this robot, if you had a big enough n by n sheet, could fold into that surface. In some sense, this is a little bit inefficient because we have n squared area here. We get only n cubes in the worst case. In the worst case, this is optimal. But we have a new method, which we haven't built as a robot yet, but just published it last year, that's very efficient. If you want to make a surface with of cubes, this surface area is 2n. Sorry. If the surface area is n, if there's n squares over here, then a strip of length 2n, so just a factor of 2, very efficient, can fold into that surface. And again, there's a font for that. You can fold any letter of the alphabet with strips of varying lengths and just very simple creases. In this case, a grid and non-alternating diagonals. And you can also write your favorite message. And this is the crease pattern. It's very long.
So one plan is to publish the longest book, and to read it, you would have to fold it letter by letter. But it's not a joke.
I mean, it is and it isn't, I guess.
Yes.
It's really going to happen. Right? So back to robots. These are some examples of real robots that we've built in collaboration with MIT and Harvard. I guess, probably most exciting robot-wise is the top right one. So this started as a flat sheet, flat laminate, and we put in 2 batteries and 2 motors, and it's folding itself. It's doing a sequence of folding instructions that make an origami robot, and about 3 minutes later, it becomes a fully functional robot with no human intervention, so completely self-folding. So now it's standing up. It's going to do a couple more locking folds, and then, or 4 minutes later, sorry. Count. And now it can walk away. So pretty cool. And that's, on the order of $10 or $20 of materials. So very simple, cheap robotic engineering. Here's again what it looks like flat. So it's just laser cut, sort of automatically assembled, and then got your robot. So that's a fun. Folding offers a new style of robot and a new style of making robots that's potentially very exciting. But one of the challenges in making these physical devices is all of our mathematical results assume 0 thickness material, which is hard to buy, but high quality origami paper is very close to 0 thickness, so it's a pretty good approximation. When you're working with metal and plastics and laminates, it's less good. And one of the first people to study the effects of paper thickness is Brittany Gallivan.
She was a high school student, and she took on the challenge of you can only fold a piece of paper 8 times.
If you're folding it half.
Folding it in half. And she had a bit of a problem because the paper that she ended up using was 3/4 of a mile long. And the first time she tried it outside, the wind was disastrous. So she finally got permission in a mall after hours with guards. And she folded it in half in the mall and then proceeded to complete the process. And this is...
She achieved 12 times, which is the Guinness Book of World Records, and probably will continue to be until they can manufacture a 2-mile-long piece of paper. And she analyzed the main challenge here is how long your paper is relative to how thick it is. That, of course, the number of layers doubles each time. That's no surprise. But that's not really the bottleneck. The bottleneck is this turning part. When you have thick material, to do a fold, you have to actually turn around. And that actually consumes length of paper. So at some point, you just run out of length of paper in the middle. You can only fold through this straight part. And so for a given design, you can compute how big or how thin do I need my sheet to be to make it feasible. And so this was a simple folding, just folding in half in 1 dimension. But we could generalize this to take a more complicated design. This is a bird-based model. Here's a crane. And if we now imagine that being made out of thick plates instead of thin material, if you double the creases and cut little holes out at the corners, then you can simulate this kind of effect and be able to manufacture really thick versions. Even though you design with 0 thickness in mind, you can algorithmically convert that into something that works for larger thickness material. Next topic is pleat folding. This is something we've explored a lot from both from art to math to 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 art to math. And we're going to show you a few of these results that we've been working on in the last 20 years. We start with this cool model, the so-called hyperbolic paraboloid.
It comes from the Bauhaus, specifically by one of Albert's class from 1927, 1928.
Very simple crease pattern. We're folding a bunch of them today in one of the working sessions. You take a square piece of paper, you fold concentric squares, alternating mountain and valley, fold the diagonals, and the paper pops itself into this intriguing 3D form. How does it work? This seemed really cool. We wanted to explore it. So we started exploring it from an art perspective. We came up with an algorithm that converts any 3D polyhedron, like a cube, into a way to join together a whole bunch of those hyperbolic paraboloid models to represent that cube. Cube, for example, has 12 edges, and so this model has 24 hypars. And in principle, this is an infinite series of sculptures.
And we've folded thousands of these squares.
Yeah. So how does this process work? We built a simulator. This is an early origami simulation. By now, there are a lot of origami simulators to see, what is the equilibrium that physics is finding when we put in these creases. And the model here is very simple. The paper wants to be bent at the creases, and it wants to be flat where you don't crease it. And then physics finds this nice equilibrium form that balances all those forces. And
as artists, it's nice to virtualize something, but what about taking the virtual thing and then making it back into reality? So these black lines represent the creases with the paper removed, and we 3D printed balls at the end, and it's taking advantage of what that construct was.
this is like a physical model of a virtual model of a physical piece of paper. But it's also like, I would call this a physical proof, like mathematical proof that we have built a computer model of this thing. Like, we understand the geometry because we could only 3D print these spheres if we really knew exactly what the geometry was, because the bars here are aluminum rods, so they're rigid. So as Marty said, at this point we've folded thousands of this model, but it turns out it doesn't even exist mathematically. It's not possible to fold anything three-dimensional with that crease pattern. So what does that mean?
That proof took almost 9 years to complete.
So I encourage you to make one because it's fun to make the impossible. But what must be going on is somehow the paper's cheating, and our best guess of how it's cheating is that it's adding extra little creases that you don't notice. So for example, if you add these diagonal creases to the crease pattern, then it does fold perfectly nicely. It's very much a hyperbolic paraboloid. But without any extra creases, it's just, you can't fold it into anything.
So we went on to curved creases, since square creases don't exist. And these we're pretty confident do exist. We're closing in on a proof. And this is also from the Bauhaus in the same era, and with a hole in the paper and doing circles radiating out, it folds into this form that we're not too sure how to describe what the form is yet mathematically.
Some kind of saddle surface.
And this is the first series that we did. These are all made out of one circle. And the difference between these three is the bottom left has a larger hole. This one's folded a bit tighter than the top one. But they're almost identical pieces in terms of scale and size and folding. And you can see the variety just of a single circle. And these three ended up in MoMA.
Then we went back to the earlier idea of combining many units together, although here just a few units. This is made out of 5 circular models. This is made out of 2. This is made out of 3. And yeah, it's pretty exciting. This showed us the sort of range of things that different forms you could make from a relatively simple pleated design. And this is very exciting from deployable structures. Maybe you want to build a space station that looks like this, then it would be relatively easy to program sheets to fold along these creases because the crease pattern is very simple. The same way you saw the self-folding robots, you could make self-folding this pretty easily. So we wanted to see what forms can you make in this way. This is what it looks like to put them together live, although this is in movie time. In real time, this takes a long time to find a happy, balanced arrangement. But if you're lucky, you get a nice 3D structure, all self-supporting. And you can make fairly large sculptures in this vein by combining more pieces. Folding makes it very stiff and strong.
We're able now, without any scaffolding or added material, to build these forms human size. And that's one of the next projects we're working on.
This is probably the largest thing we've built, and this is what Marty's office looks like. You should come visit. And we're looking at all sorts of ways to combine these forms. This is the two of us taking duct tubing, which is also a pleated structure. It's concentric circles, in fact. And then we take our paper folded models, and they perfectly join 2 tubes together.
This is 2 times real time, but there is kind of a trick involved here. The point of this is to show that we collaborate really well even when we're not talking. Kind of mind reading, everything's perfect. Did anyone see how we did that so well?
Maybe play the beginning, it's the most obvious.
So it took too long to build, so that we did a video of taking it apart and then running it backwards.
The tube just knows where to go. This is the final model, so it's got quite a bit bigger, and it's a lot of fun to play with. Here's some experiments in Photoshop, playing with photographs of these models and really highlighting the different shadows you get to accentuate the pleating. This is a totally different way to look at curved crease sculpture, which is in X-ray video, which you don't usually see.
Erik is a qualified X-ray technician now.
So we took actually 3-inch curved crease model, and it's on a turntable rotating, and you're looking at the X-ray image through that. And you see these cool zigzags. Even though all the creases are curved, you can see the pleating as like a straight line.
What's exciting about this is that we have, in the scan, we can get any XY frame and tell where all the paper is, and we can now build out of other materials by using this process.
Right, this is a fancy way to do 3D scanning with complicated geometries. Okay, time for some glass blowing. So this is Marty blowing glass blindfolds. Don't try this at home.
So working in these two different mediums, we would like to combine them if possible because we love both of them. And in this video, I recognize that paper's all done by touch. And glass blowing, you can't touch. But if I made myself blind, I would have to rely on touch to become more sensitive to the material. And here it is being shaped by some wet paper, which is kind of another way to adjust it. And there is a spotter in case I do something bad.
But surprisingly, this is one of the few times Marty did not burn himself.
And that's actually true, because glass blowers don't mind little burns. But I don't know if you noticed, there's little cement blocks on the floor that I would wedge my feet into. I'd kind of inch up and find the spot.
So we made a bunch of these glass heads, call them, and then here's what it looks like to put concentric circular creases into it.
Right? We've been getting that question a lot. So this is how it's done.
Of course, in real life, this could take hours, but in movie time, it's instantaneous. And as soon as you put the creases in, it pops into this 3D form. If you fold it really tightly, you can put it through a very small hole in the bottom. And once it gets in there, it kind of opens up naturally to restore equilibrium. That way you can get a kind of ship in a bottle. And we've been playing with this idea a lot over the years and making more complicated, intricate glass forms and then more complicated, intricate paper forms to put inside. And there is one in the exhibit here. So
Two. There's two glass forms.
Right, two. So you can go see what they look like in real life. These are fun because they're actually, the glass is folded. So these started as long tubes, and then they got folded in half once. So you know that it goes up and around like that. You can also make functional glass forms and fill them with paper. This is like a teapot, but it's not actually functional because there's a hole in the bottom, and there's no hole here, and there's no hole here. But other than that, it's great for storing your paper tea.
We're starting to work in other materials. We've been doing linen and velvet. These are two velvet pieces that we folded. And the velvet one, we had to cheat and put a piece of paper between two pieces of velvet to get the same properties.
Also with the linen, there's paper in between two layers of linen. Here we're also combining with string, skein. And most of our artwork lately has been experimenting with printing different patterns onto the piece of paper before folding it. And our first instance in this series is called Destructor. So we want to, what should we put on the piece of paper? And there's this short story called The Destructors by Graham Greene in
1964, I believe.
And if you've ever seen the movie Donnie Darko, this is the story that they're reading in Donnie Darko. And the theme of Donnie Darko and of the Destructors is that destruction is a form of creation. So we took that as permission to destroy this story and turn it into sculpture. And if
Now,
you...
the story is still there, so if you destroy the sculpture, you can read the story again if you want.
can unfold it. And we can also put that in glass, and this is another Donnie Darko reference. And so we're going to show a bunch of examples of this. Here's one with a QR code. This is sort of a computer science topic. QR codes are written with an error-correcting code. So you can cut a big circular hole out of the center, and this thing will still scan. Given enough time, your phone can scan this, and it will say, folding error. So folded, however, it does not scan. So this is putting some sheet music onto a piece of paper.
We were invited to submit a piece to a show called Nothing. And so we ended up, it was a struggle. We came up with a lot of ideas, and we finally decided on using the music Nothing from Nothing, which is the first music that was played on Saturday Night Live, to kind of honor Billy Preston.
And we made something from nothing from nothing. And we were wondering, should we put a speaker inside that plays the music? How can we actually connect this to music? So we ended up turning the piece itself into a musical instrument. So it's a percussion instrument, but you can play it in many ways, like a washboard, or you can just hit it really hard. The strikers here are actually made from the same paper. Get the idea? So these are some pieces about translation, I guess, and calligraphy. We're invited to a show in calligraphy in the UAE. And if you look closely, the creases alternate between Arabic and English for the same text. Here it's saying art through words, and here it's saying calligraphy, literally. So that was a lot of fun. Okay,
And
on
then
back to
we
glass.
decided to make them in glass.
Right.
And this was kind of the ultimate challenge, because glass doesn't move the same way. You also can't hold or touch it. But we achieved some interesting forms, and we had help with Jeff Ballard and Manny Krakowski.
Two amazing glass blowers. So here's what the process looks like. This is the glass blower's concentric circles. You start with these cylindrical tubes of glass, which you make by just pulling a cylinder really long. It's called glass cane. Here it's all clear. And you take this disc of glass and are going to roll it, and glass sticks to glass. So it's going to roll along here. This is pi long. This is radius 1. And you end up making a cylinder with lines along the outside. Then you stick a tool in here and flare the whole thing open, and you get concentric circles.
So we're halfway there.
So these are like ridges. Yeah, and the last part
is we're back to folding by hand. So we put on some Kevlar gloves, and you have, 4 or 5 seconds till they start to burn.
Yeah, don't inhale burning Kevlar. It's not very nice.
Kevlar is not the best to breathe.
And if you get it right, it folds the way you want it. If it doesn't, you have to start over. And then with enough experiments in that, you get these really cool transparent material. You get these cool interlaced patterns. It's a lot less flexible than the paper models, but you can still assemble them pretty well. And this is an example of a broader notion of glass folding, which we've been exploring a lot with Peter Hauk, who runs the glass lab at MIT. In particular, pleat folding again. And so these are made by taking hot glass and wedging it into a mold, like in the top there. And then you can, again, pick it up with your Kevlar gloves and shape it a little more, give it some twist or fold it more or less. This is the making of that stem in a goblet. And then you can combine this with more traditional glassblowing techniques, make vases with folded structures and all sorts of fun things. But glass folds very differently from paper. We're always looking for different ways to combine paper and glass.
So we've been combining cold glass with paper, but what about hot glass with paper? So this is our first experiment. The paper's been wet, and then we're just pouring glass on top of it, experimenting, learning how to do it.
And it just burns the surface of the paper, not all the way through, even though it's 2,000 degrees Fahrenheit. And you get these really cool over-under patterns. There's a known mathematics to how things coil. So like this is like when you're dripping honey off of a spoon. It depends on the height of the drip, and you can get these kind of coils all to one side or the alternating sides. And so we have global control about where we want this thing to go, but the glass also has its own like local patterns that it wants to do. And so we call these pyro prints. Here's us making these together. Got to be careful not to hit each other. And there's a picture. Well, these are the sorts of things we get from that process. And then to close the loop, we can take these prints and then fold them. So this paper folded from, that's been burnt by glass, and then folded into paper, and then inserted into glass. Yes. When did we start? My watch says, you're doing a dynamic workout. Good job. I'm jumping around a lot.
I think close to 15 after.
Cool. Okay. Well, we should probably start wrapping up. Our last topic is glass cane again. This is an example from very early glass cane. This is, again, the tubes of glass. Here's a little idea of how it's made. You start usually with colored glass in rod form. This is Lino Tagliapietra, the best glassblower in the world. And you make these cylinders, in this case in color. Then you can arrange those cylinders and pick them up into glass again. So it's cooled down, and now I'm going to roll hot glass onto it. And now we've got those lines arranged in a circular pattern. If you pull it again, but this time twist it, you can get some really beautiful crisscross patterns in that glass. And if you've ever seen glass work like this, that's how it's made. That pattern is probably this like dark pattern. There's another one for making this blue pattern. So these are this is a beautiful style of glass making, sort of on the more complicated side. And there's a standard set of patterns that almost everyone in glassblowing
Not just
uses.
a standard set, it was assumed that there were no other patterns at the time. The last ones were designed by an Italian dentist, but no one really believed it. And
So we took this as a challenge to design new patterns, and we wrote software which you can all play with called Virtual Glass. Get it at virtualglass.org. Design your cane in cross-section, and then see what it will look like pulled and twisted. And you can use this to find patterns that look very different from existing designs, see what it looks like on a final piece. And so 3 of us designed a few different designs that look fundamentally different from existing designs out there. And then at the Museum of Glass, we made them, and they look pretty awesome. And by now, lots of people, it's been around for about a decade, and lots of people have tried their own glass cane designs. These are some designs made by non-glass blowers, so this makes it really accessible. Even though it can take years to learn how to pull cane, now you can see what it's going to look like. And of course, we made a font. So again, this is what the cane looks like in cross-section, but it's pulled and twisted, and so from the side, it's almost unrecognizable. Some of them are classic, like this O design is what you saw made in the video. Another classic one is the I design. Those are the only 2 that exist in the glassblowing literature. But this is, let's see, we can write USD or something in, maybe, yeah. cane. And you can also fold it again. So this is to close all the loops. We have a circular piece of paper with the entire alphabet A through Z written twice, folded into a piece. And a piece like this is on display here. And
Exactly that piece.
this piece and this different one, I think.
Different
of this
one.
But you can also insert it into glass. Again, this looks like twisted cane. And that's what we wanted to share with you. Hope you enjoyed.
Thank you.
You can see why we think they are we have time for a handful of questions.
Yeah.
Is there any possibility of making this create livable space?
Livable space by folding. Sure. Yeah. There's a lot of interest in building sort of mechanical and architectural scale structures that, yeah, you could imagine in your suitcase having your house and you unfold it when you go to the beach or something and you have your nice pavilion, that sort of thing. There are a bunch of examples of that, although there's still a lot to explore. Yeah. So the question was, if you have a polygon and you look at the creases that go to a vertex, is it always an angular bisector? And I think if there's only one crease at that vertex, then that has to be the case, because locally you have to fold this line onto that line, and the angular bisector is the only thing that does that. But if you have many creases going to that point, I think you could do something else. You could simulate the effect of that one crease by a sequence of other reflections. But the method we have for solving this problem does have that property. It uses angular bisectors, not just at vertices, but also, like, if you have two distant edges, you want to fold them onto each other, you fold a generalized angular bisector. And in some sense, we just combine a lot of those to make it work. Although details are a little complicated, that's the heart of the idea. Very good. Yeah. 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 So what about externally folding paper robotically? There's only one robot that I know by Devin Balcom for doing this at CMU, and it was an open loop system. So it would take a sheet, it would like suction to pick it up and place it, and then there's like a wedge that would crease it, push it into a wedge, and you could fold it and then rearrange. And that's works for making simple folds, just folding one crease at a time. The trouble with paper, especially paper, it might be easier if you're folding metal or something. And there are robots for folding metal and along curved creases. But paper is super flexible, and so to do more complicated folds, you really need to keep track of like where everything is at once, and we just don't know how to do that. Humans do it really well. They say, oh, this is just out of the way. I got to push this, and it's different every time, even if you're folding exactly the same model, because there's a lot of ambiguity in how paper folds between the creases. I think that controlling that is still a mystery for us, even geometrically. In fact, the paper with Satyan was kind of about this process. How do you, if you have full control and you can move every atom of paper, how would you control it to go from shape A to shape B? And we have a method to do it. It's a terrible method. It's impractical, as he said, but it shows that there is a way to do it, but we don't know nice, elegant ways. And even harder is to do it with a limited number of fingers. So there are lots of interesting open problems there.
Well, Ben
Yeah, definitely in art, we love to play with ambiguity and exploiting it, but also having a mixture of control and ambiguity. But robots deal with ambiguity very poorly. So in that setting, you really want to understand everything. Both sides are interesting, or any point on that continuum is interesting. Mathematics tends to veer towards the full understanding, but it's hard, and so reality is somewhere in between, and art maybe likes to go more ambiguous.
But I like your suggestion that we should train robots to do that kind of art.
Yeah.
Kind of allow a structure to kind of take on
Right.
not necessarily a robotic imposition.
Yeah. Yeah.
So the circular, what happens with the scale of the regularity? So if you make the folds, for example,
Yeah, we've done experiments. We've also introduced like doing a half circle with a straight corner at the end. And everything seems to work reasonably well. The circle, I think we do more than any other because we're trying to understand that one first. And we think we can use that to quickly generalize to the other forms in terms of mathematical understanding.
One of the surprising things that's not obvious at first glance is that a lot of the variations you described produce basically the exact same shape. So it's surprisingly robust. Not everything you change makes the same thing, but moving creases small amounts in different ways surprisingly doesn't change it very much. So it's somewhat stable. But there definitely are ways to control the shape, and we'd like to understand them all. Yeah. Well, they say the best way to predict the future is to make it. And so, I think the big message here is we're trying to fuse together art and science, that instead of having different people work on different fields, the Renaissance vision is to work on many different fields at once. There are a lot of good reasons to do that. One is that you have these traditional disciplines been around for a long time, and people don't usually look in the cracks in between. And there's a lot of exciting new research that should be done between any two fields, I would claim. And so if you know one, you should learn another and look at those interdisciplinary things. This is why people are excited about interdisciplinary work. But also just practically for us, it's a lot more fun to work on something and not get stuck all the time. If we were just doing mathematics, a lot of these problems are super hard, and we would just hit a wall, and we'd have to switch to a different problem or just bang our head against that wall. But now we have all these other ways to express the interesting things we're exploring. If we can't do math, we can make a puzzle that shows why this problem's so hard, or we can build sculpture and through that sculpture get intuition about how to solve the mathematics, or we can make a font, and vice versa. We have ideas for sculptures we want to build, and it leads to new math problems. So, does this thing even exist? How could we compute it? And then now we're into a math problem of how to represent that sculpture, so we can, from art we get new math, and from math we get new art. And that back and forth, I think, makes us a lot more productive, even if we were just working in one field. So the hope is that the future will have many people like us that do that. So please follow your own passions and combine different things together. And collaboration is a great way to do that. Then you get all the tools that we each have. In the back. Other passions. We've both done improv comedy.
Yes, we've performed on stage. We're also interested in film and video.
Yeah.
We've been doing experiments with that. And
we made a film about Lino Tagliapietra, which is what we were showing an excerpt from that you can see online. We like magic. Anything that's fun is our guideline. But of course, different people have different things that are fun.
Yeah, so I don't think we're fixed at all. Tomorrow I might be interested, or we might be interested in something totally unexpected.
We also play with puzzles, as you kind of briefly heard, and I play video games a lot. But we also study puzzles and video games mathematically. And on Saturday there's an MAA meeting here. Where's here? And I think at 9 a.m. then we are giving a talk about the games and puzzles research. So if you're interested in that
just
side.
games and puzzles. Wow.
Yeah.
Video games.
Yeah. Tetris, Mario Brothers, Mario Kart.
So it'll be a very different talk.
On that note, we try this here.
Thank you.